All right, so did everybody get a worksheet for today? We're going to start out with our concept review questions for last week's lecture. There's quite a few of them since we covered 2 chapters last week. So a circular loop of wire is in a region of spatially uniform magnetic field. The magnetic field is directed into the plane of the figure. If the magnetic field magnitude is constant, what would you say about the induced EMF?
Constant?
Where does this chair belong? All right, who's ready to vote? Everybody's ready to vote. You can shout it out loud if you all have the same answer.
C.
See
that? I knew the homework.
I know. Well, good job. As Vin said, the induced EMF is 0. Why is it 0?
Because the magnetic field is constant.
Magnetic field's constant. Yeah, there's nothing.
It's constant, the coil's not moving.
Coil's not moving. Yes. Okay, next one. A circular loop of wire is placed next to a long straight wire. The current I in the long straight wire is increasing. What current does this induce in the circular loop?
Increasing?
Yeah. Can't tell if people are thinking or bored. So who's ready to vote? All right, well, we'll go ahead with it. Who thinks the answer is A? 1, 2, 3, 4, 5, 6, 7, 8. Okay. Who thinks the answer is B? Who thinks the answer is C? Who thinks the answer is D? Okay, so 8 people voted and 8 people chose A. So why did you guys choose A? Chris?
So I used the modified right-hand rule. So the current is going in this direction, so the B field kind of curls under and is coming out of the board.
Okay.
So since that's increasing, the induced magnetic field is going to want to resist that. It's going to go into the board.
Okay.
Then I use the right-hand rule again and put my thumb into the board, and then fingers are going to curl around in a clockwise direction.
Okay.
And that's the way the current will go.
All right. Did anyone else use the same method? Did anybody use a different method?
Yeah, I just remembered that when you have 2 wires together and there's induction going on, the current that is induced in the second wire is the opposite direction of the current of the first wire.
Okay.
Principle.
Okay. Cool. Anybody use that method? Okay. That's 2 people and 2 different methods. So anybody else? How did you come up with the answer A? Guess. All right. Anybody else use the guess method?
Me too.
Oh, okay. All right. Well, so we've got a couple explanations. Are people satisfied? Do they feel like if they guessed, they understand it now? Okay. Any other questions?
Yeah, I don't understand how you do that with right-hand rules.
Okay. So we're just using our modified right-hand rule with the thumb and the curling fingers.
Yep.
So we put our thumb in the direction of the current, and that tells us that the B field above that top wire is going into the board, and below that wire it's coming out of the board. So you've got B field coming out of the board through the loop, and it's increasing. And we get induced currents in B fields that want to resist change. So if there's an increasing B field, then an induced B field will be created that opposes it, because it says, I don't like the increase, so I'm going to make a B field that's opposite to that. So if you've got an induced B field that's into the board, then we use our modified right-hand rule again. Now we can put our fingers in the direction of the B field, and our thumb curls around in the direction of the current. Or you can use...
How does that show it's clockwise then?
Because my thumb is going around in a clockwise direction. If my fingers were coming out of the board, then my thumb would be going around in a counterclockwise direction.
Okay.
So,
Isn't the curl of our fingers of the induced B field this time?
yep. So my fingers are for inside the loop, because that's the only part that cares, is the inside the loop. That's where you have your area, is inside the loop. So I'm curling my fingers around the edge of this wire. My B field is coming, well, it's going into the board. My induced B field's going into the board. And so my thumb is the wire, and my thumb curls around like that.
Okay, clockwise.
Yeah.
Yeah. Okay.
Cool. Okay. A loop of wire is being moved to the right at a constant velocity. A constant current I flows in the long straight wire in the direction shown. What is the direction of the induced current in the loop? Okay, who's ready to vote? 3 people? 4, 5, 6, 7, 8.
I'm not sure about the orientation of when you're pointing at the induced field. Which way do you put your thumb? Because this is omnidirectional when you're pointing at the B field.
It depends on which side of the wire you are on. So if you're like your hand looks like it's going into the board. So down here, my thumb would be going to the left along this wire. Here would be going up. Here would be going to the right.
So top of the hand remains towards the inside of the object? Like
Yeah, always inside the loop, yeah.
Okay.
All right, who thinks the answer is A? 1, 2, 3, 4, 5, 6, 7, 8. Who thinks the answer is B? 1. Who thinks the answer is C? Who thinks the answer is D?
I go for B.
Okay, 2 for B, 8 for A. So why did people choose A? Go ahead, Chris.
So I use my right-hand rules again. Slow. So if the current is going this way, and the current is constant, then the B field curling around is going to be heading into the board. And since it's getting left, the magnitude is decreasing as you're moving away from it. As the loop is pulled away, the amount of B field that's within the loop is going to decrease. So it's going to want to resist that. So it's going to induce a B field into the board.
Okay.
So then I put my thumb into the B field, curl my fingers around, and that would be clockwise. I do it a little bit differently. I just use my thumb.
Yeah, it works too. Yeah,
little monkey fingers, you know.
and that works. What Chris is saying is with the modified right-hand rule, this can be B or I, or this can be B and this is I. It doesn't matter. It works both ways as long as you use your right hand. Yeah. Good. Did anyone have another method of getting to the same answer? Okay, so how many people used Chris's method? 1, 2, 3, 4, 5, 6, 7. Okay, so that was the chosen method for A. People who chose B, do you want to make a case for B? Nope.
Yeah. Because with right-hand rule on the pole, if current's going up, then the field is going into the square. Then the opposite induced magnetic field, then you point at that with the inside of your hand to the inside of the thingy, the square. Then your thumb's pointing down, which is counterclockwise.
Okay, so the difference is you decided that the induced B field was out of the board, and Chris decided the induced B field is into the board. So what determines the direction of the induced B field?
Well, the B field's still into the board.
Which B field? The induced B field or the B field?
The regular.
The regular B field is into the board, but you decided
Oh, okay.
that this is the part that's different. You decided that the induced B field is out of the board.
Yes.
Chris says the induced B field is into the board.
Okay.
So what determines the direction of the induced B field?
Is it opposite of the regular?
Not necessarily. When is it opposite?
When it's increasing.
When it's increasing, yeah. If it wants to oppose any change in B field. So if the B field is increasing, then it would have an opposite direction to decrease it back to at the regular level. But if it's decreasing, then the induced B field is in the same direction because it wants to keep it at the same level. So whatever it's doing, it wants to stop that change. So in this case, the B field is decreasing as we pull that loop away. So the induced B field is going to be in the same direction because it wants to boost it back up to the same level it was at.
To amplify it.
Yeah, yeah.
Okay.
So, but your logic was good otherwise. So you got the right direction based on the idea that the induced B field would be out of the board. So, all right, let's double check since there was some dispute. So the book does say it's clockwise. Okay, same picture. Now the rectangular loop is being moved to the right, a constant current is flowing, blah, blah, blah. What are the directions of the magnetic forces on the left hand and the right hand sides of the loop? All right, who's ready to vote? 3, 4, 5, 6, 7, 8. Okay, who thinks the answer is A? 1, 2, 3. Oh, wait. Nope, just one. One for A. Who thinks the answer is B? 1, 2, 3, 4, 5, 6, 7, 8. Who thinks the answer is C? D? Or E? Oh, no E. Okay, so 1 for A and 8 for B. So we'll start with B. Why did people choose B?
I used the right hand rule where the finger was current and law, and yeah, and so the thumb was pointing outward on the left side and outward on the right side, so it's left on the left, right on the right.
Okay.
Yeah.
And anyone else use Thomas's method? Wes used it, Chris used it, Jeremy used it? Yep. Okay, anybody use a different method? Okay, so that's why people chose B. Jordan, do you want to defend A?
Well, I use a method too, but it's, so index finger current, middle finger B field, thumb is force, right?
Mm-hmm.
So that would mean that the left wire is going to the left. So do we agree on that one?
Mm-hmm.
But then when apply that also to the loop, because the loop has a clockwise direction. And I'm just looking at on side B, the current going that way. My hand rule looks the same. So according to that, I conclude that that's also going to the left.
I think you're misreading it, because it's asking about the left and right side of just the loop. So it's not asking about the force on the wire at all.
Oh, okay, hold on. Yeah, okay, so it would be B then. Okay.
All right, all
I
right.
misread the question.
Yeah, no, that's fine. Okay, so another way to do this nobody mentioned yet is if you just remember that parallel currents attract and anti-parallel currents repel, then you get to the same answer, since the closest side of that square is got a parallel current and the farthest side has an anti-parallel current. So all good either way. So correct answer was B. Okay, 30.1. A small circular ring of wire is inside a larger loop of wire that carries a current I, as shown. The small ring and the larger loop both lie in the same plane. If I is increasing, the current in the small ring has what? Okay, so there's some things we didn't talk about. So I guess ignore the A, B, C, or D, and we'll have answers A or B. Clockwise or counterclockwise. Those are your options. A or C? Wow, I'm doing great today. A or B? All right, who's ready to vote? Okay, who thinks the answer is A? 1, 2, 3, 4, everybody. Who thinks the answer is B? Okay, so why do people think the answer is A? Why is it clockwise?
The current's increasing to the left, so it wants to oppose the increase, so it decreases to the right. Or increases to the right to oppose the increase to the left.
There you go.
Yeah.
Okay, so did other people use that line of thinking? Okay, did anybody use something slightly different? Chris, what was your approach?
I just always default to the right hand rule.
Because you love it.
I just love it. This company's like a blanket.
Yeah. So go ahead. Do you want to explain it, or is it self-explanatory?
So, yeah, the currents, I just used, because it's a loop, it's always going to be heading in that direction. So the B field that's generated by the large loop is going to be coming out of the board. Since it's increasing, the induced B field is going to be into the board. So then the induced B field and then the current, the smaller ring would be. Okay. Anybody have any questions about what Chris said?
Doesn't that show that the current would be going to the left if the induced is going into the board?
If it's going into the board, then my fingers are curling around to the right like this.
Yeah. And then that's
Which
the
is
current.
clockwise.
Isn't
B field, current. B field, current.
Oh, this is your B field now.
B field.
It doesn't matter either way. You can, with this right-hand rule, it doesn't matter.
Yeah, same thing.
Yeah. So you can make this your B field and your thumb your current, or you can make this your B field and your fingers your current, and it works.
Okay, so what if my multiple fingers are
The B field. So the induced B field's into the page, and so your thumb is curling around in the clockwise.
The top of the hand's the inside of the object.
Yeah.
Oh, okay.
Yeah.
All right.
All right. Okay, 30.2. A current flows through an inductor in the direction from point B to point A. There is zero resistance in the wires of the inductor. If the current is decreasing, what can you say about the Well, which answer is correct? There's various options. Okay, who's ready to vote? Okay, most everybody. Who thinks the answer is A? 1, 2, 3, 4, 5. Who thinks the answer is B? 1, 2. Who thinks the answer is C? Who thinks the answer is D? Who thinks the answer is E? 2. Okay. All right, so we'll start with A. Why did people choose A?
The inductor is going to want to keep the same amount of power coming out of it,
Okay.
ignoring the change of the input current.
Okay. So what does that mean?
It'll eventually drop, but that should make the potential higher at point A
Why?
because it's trying to resist the change in current.
It's trying to resist the change in current. So what direction would the EMF be?
Towards A.
Okay, so the way we drew that last
Unless
week
I'm
was,
wrong and it's trying to output in the opposite direction, like the feedback you talked about the other day.
okay, so that's, I'm just going to write down what you said. Okay, to try and visualize what your argument is in terms of potential. So your potential you think is towards A, and so that would create the increase, a potential increase from B to A. Sort of like when we draw that plot, like it's climbing a mountain from B to A. Okay, so that's Wes's logic. Did anyone who chose A use the same approach? What about different ways to get to the answer?
I was just remembering a homework problem. Assuming I did the homework problem right.
Oh, so this was reminded you of a homework problem. That's how you got to the answer?
Yeah.
Okay.
I just remembered the little, that image, and on the other side where the current was flowing, the potential was just higher. So, for whatever reason, that was the case in the homework problem.
Okay. Did anyone use another method to get to answer A? Okay. So that's why people chose A. How about B? Why did people choose B?
Well, I was thinking, like now that I think about it, there's no resistance, so there wouldn't be I was thinking drop, but there's no resistance, so there wouldn't be a drop across it. So I think I'm changing my answer.
Okay. Do you know where you want to go with your new answer?
Yeah, to E.
To E? Okay. We've got a defector from B. Anyone else who chose B want to defend B?
I was kind of thinking the same lines as she was, but I am indecisive.
So you're now in no man's land, but nobody wants to support B. Okay, so we have some people chosen E. So why did people choose E? That means both C and D are correct.
I remember the equation for voltage across an inductor is L times di over dt. So the opposite combination of C and D.
So, the voltage across an inductor,
Yep,
the EMF. Okay.
Kind of just the opposite of L.
The opposite of L? What do you mean?
The opposite of the inductor, just from the sheet here. The opposite.
Or negative.
Oh, negative. Okay, so what does that equation tell you? It says that the answer depends on the magnitude of di dt compared to the magnitude of I. So if your EMF is described with this equation,
What it means is that when your current is constant, like at DC, then you're going to have no voltage difference between A and B. You know, because
True.
the derivative of a constant current is just going to be 0.
right,
But as it's changing, then you're actually going to have like a slope value, and that's going to give you a constant when you take the derivative. And then
Okay.
multiply by the inductance, and it tells you your voltage potential across A and B.
so what about in this instance where it says the current is decreasing?
Well, yeah, this is kind of where it was a little weird because A, I think, is going to be like true in this case as well, because this basically turns the inductor into a current source, and it is going to produce an electromotive force in that direction. I just thought that E was the more correct answer to describe what goes on in an inductor.
That's true, that does fully describe what happens to an inductor, but when you say the one instance where the current is constant, then you don't have any potential between A and B.
And in this case, it's saying it's decreasing.
Yeah.
The equation still describes it.
That's true, but your answer wouldn't change. For the case where the current is decreasing, the answer wouldn't depend on the magnitude of di dt, since in every instance where I is decreasing, you have a non-zero di dt. So that's my argument against C, but you guys are welcome to disagree with me.
Well, the equation describes it no matter what the case is. You know, whether it's increasing, decreasing, or 0, they're saying the same.
But for the case where the current is decreasing, this is saying that you might have a potential that goes from A to B, or you might have a potential that goes from B to A. That's what C is saying, that the direction of the potential could depend on the magnitude of di dt. So does the direction that the potential goes in the case when the current is decreasing depend on how it's decreasing? Or is the direction always going to be to the left?
It would be to the left in this example.
That's what I would say, because I would say if it's decreasing, it wants to boost that current. And so in every instance when it's decreasing, the EMF would be to the left. I can't think of any instance when it's decreasing current when you'd have an induced EMF to the right.
So are you saying that the equation doesn't account for the direction? Is that what?
The equation itself, I think you have to use your own logic to figure out the direction. But this question is basically saying between answers A and B, the EMF is going to the left or the EMF is going to the right. Or sorry, the other way around. The EMF is going to the right or the EMF is going to the left. Answer C says that depends on the change in current, di dt, compared to the magnitude of the current. And I contend that as long as the current is decreasing, then the direction of the EMF is not going to change. It will always be in the same direction. So this maybe it's just the confusion about what this question is asking. It's just asking about the direction of the EMF. It's not asking about the magnitude of the EMF.
That's what that's saying?
So it's just saying, is the potential, basically, is the EMF going to the right? Is the EMF going to the left? Or does the direction depend on how the current is changing? Or does the direction depend on the value of the inductance? Chris?
So I have a question, like a clarification question. I selected E because I wasn't 100% sure, and I was just looking at the formula, and it looks like it depends on both of those things. Now that you've explained it, it makes sense that because of the opposite sign, because of the negative sign or opposite sign or whatever you want to call it, if the change in current with respect to time is decreasing, so it's negative, that's going to make the voltage positive, which means it's going to be positive across in